Good morning, everybody. Welcome to our webinar on why speed of measurement plays an essential role in automated metrology systems. This is the second in our series on automated metrology. If you have any questions, you can enter them into the chat and we'll scroll through in the Q&A and we'll scroll through them at the end. We'll definitely save some time for Q&A at the end. Perceptron was founded in 1981. We have over 2,700 installations worldwide at manufacturing facilities, helping them with their productivity and quality, with automated metrology and also vision-guided robots for adaptive manufacturing. You don't need to look any further than the current global pandemic to realize how important data is. Imagine if we had 100% real-time data on infection and how that would change everything about our current situation. When we talk about speed of measurement, we are specifically talking about the speed at which an automated metrology system can measure the critical characteristics of your parts and the ability to report that data back in real time. Now, if you're already measuring 100%, you already understand why speed of measurement is important for inline systems. The faster the measurement acquisition, the more measurements you can collect within your cycle time. But often when quality departments buy nearline or offline equipment, they think that cycle time is no longer a priority. If your nearline systems takes 10 or 15 minutes to measure one part, and when I say measure, I mean collect and report the results, this places a severe limitation on the number of parts you can sample per shift. And today we're going to talk about why that's important. My name is Rick Van Valkenburg, and I'm here with Dr. Jim Roan. Jim has been solving manufacturing problems with data since he started pursuing a doctorate in the subject at the University of Michigan back in 1990. And while I'm currently responsible for sales and marketing at Perceptron, my first role at the company in 1996 was as a project engineer working directly with customers, process and product engineers doing tooling repeatability studies. We would temporarily set up Perceptron sensors in each geostation, put targets on the parts being joined, fixture those parts, measure, unfixture, and then repeat that process 25 times. If the tools did not pass the repeatability requirement, we would shake down the tool, miking pins to make sure they were not undersized, shimming clamps to metal, checking clamping sequences, etc. And having results go from over a millimeter Six Sigma to 0.15 Six Sigma as we made specific tooling changes. That was made possible by the amount and quality of the data being generated. In the first webinar in this series, we talked about the value of absolute accuracy in automated metrology. That is, traceable accuracy as an integral part of the system without offsetting to some external measurement device, such as a CMM. In this webinar, we'll focus on the importance of speed of measurement. Now, when we talk about automated metrology, we consider automated metrology to be on a continuum from less automation to full automation. On one end, you start with a traditional offline CMM in a temperature-controlled environment. You move towards a nearline measurement system where you're out on the plant floor next to the production lines. And at the fully automated end, you have absolute accurate, robotic, inline, in-process measurement on every part. If your system isn't in the process, then there's an operator manually loading a part, pushing the start button, and waiting for the system to complete the measurement routine before measuring another part. One key benefit to automating is increasing productivity by reducing the manpower and also the expertise required to collect dimensional data on your process and product. This is a picture from a desk calendar I received from the marketing department of one of the world's largest metrology companies. Somehow, they think it's a benefit, something to promote, that you have to complete these tasks before you start producing data, as if the measurement process itself was the product and not the data. You see this quite a bit in the metrology market, where there are resources dedicated to collecting data and different resources dedicated to using data. When your job is only collecting data, you focus on the measurement system's features. But if your responsibility is using the data, you focus on the value provided by the data and achieving the best possible quality at the lowest possible costs. Here is one of my favorite pictures of one of our inline system installations. These guys are in the middle of re-aiming Perceptron sensors to a new model after the equipment has been measuring parts in this manufacturing environment for 7 years. It reminds me of the quote that opportunity is often missed because it's wearing overalls and looks like hard work. Our equipment is made for the plant floor, and we have project execution resources worldwide. Our inline and nearline systems are configured to comply with plant standards for robots and PLCs. When a customer requires measurement on every part and they have very limited cycle time, we install fixed sensor systems. We have fixed sensor systems today measuring 70 features in under 10 seconds because of cycle time constraints. That said, most of the systems we sell are robotic systems. And this is driven by the need for flexibility. The need to measure 4 or 5 plus 1. That is 4 or 5 production models plus a pilot model. When we add absolute accuracy to these systems, our customers often want us to measure a production routine, a long routine, and a scan routine. A production routine that can measure the most critical features within the standard cycle time, a long routine that can measure all the features they require at a break or lunchtime, and a scan routine on any problem areas they may be investigating, such as a tail lamp can or sunroof opening, where shape is critical. A standard 4-robot Perceptron system with AccuSight can easily measure over 1,000 features in a 15-minute production break. This is a game changer. I had a CMM expert tell me once that CMMs measure way more than a Perceptron system. And what he meant was that while an inline Perceptron system may measure every part, it had a limited amount of checkpoints, whereas a typical CMM program was measuring 500 to 1,000 features. But now, without having to take a body out of the line and move it to a temperature-controlled room to be measured by a CMM, manufacturers can accurately measure the same number of features from their inline system at break or between shifts, or if they're blocked upstream. Now, as noted, an inline system that measures every part has limits on the number of features it can measure within cycle time. So if you are following the methodology outlined above, where you have a production routine, but also a long routine, you need to consider your sampling requirements for the long routine. In the same way, if you have a nearline system, you are sampling, and you're using it to manage and monitor your quality. So how do you think about your sampling measurement requirements? In general, you need to measure enough to have confidence you are building what you think you're building, enough to know your process is capable and stable, enough to satisfy your customers' requirements. In other words, you want enough data to improve your quality, but you also want enough data to prove your quality. Yeah, enough so you can solve most build issues with data that you've already collected, and enough to anticipate and prevent failures. That is, use the data to be proactive. Now I'll hand this discussion over to Jim to discuss some ways to assess your sampling strategy and requirements. Jim?
Thank you, Rick. Good morning, everyone. As you know, for mass production manufacturing process, the advantage of 100% inspection consists of able to identify every defective and non-conforming part, able to immediately classify any special cause, sudden process changes, for example, mid-shift, outlier, bimodal distribution, multiple tooling issue, and so on. With the availability of 100% data, users are also able to verify tooling move once the part is measured by Perceptron inline system. And another advantage is to have accurate information on your process mean and Six Sigma variation. Therefore, inline measurement system is always the first choice for manufacturers if a condition are allowed. On the other hand, sometimes because of an economical reason and the space limitation in the assembly line, only nearline or offline measurement devices are available. As a result, user can only do sampling measurement instead of a 100% inspection. So when sampling strategy is applied, typically, traditional SPC sampling control chart can be used to determine whether the process is in control or not. In addition, user may ask some other questions, say, for example, if I'm making 100 parts in 2 hours of production, how many parts do I need to measure? From those limited number of parts I can measure, how much confidence do I have if I want to estimate my process mean and process variation during those 2 hours of production? I'm going to use the following 2 slides, which are based on statistical estimation and the hypothesis to illustrate how many parts we need to measure. So the slide we are showing, let me see if I can steal Rick's mouse. The slide we are showing represent 95% confidence interval of the absolute value of the maximum difference between sample mean and process mean. So horizontal axis is 95% confidence interval, and the horizontal axis is the sample size. Those curves in the middle represent different Six Sigma value from 1.0 up to 4.0 in Sigma. I will use a couple of scenarios to explain how to use this chart. Example 1, if I'm using a Perceptron nearline system to measure part, or from the assembly line, I measure the first part from this morning's production, finish measurement, put it back to assembly line, grab the second one from assembly line, measure it, put it back, and so on. After I finish measuring 10 parts, for example, in about 2 to 4 hours, I can calculate sample Six Sigma for those 10 parts. If the sample Six Sigma value is 3 millimeter. Okay, so now we have a sample size of 10, sample Six Sigma 3 millimeter. Let's look at the chart. With a sample size of 10, I can draw a vertical line going up, intersect with the curve of Six Sigma 3 millimeter. At the intersection point, I can draw a horizontal line to the left, intersect with the vertical axis, which is about, looks like it's about 0.36 millimeter. So this 0.36 millimeter means with a confidence level of 95%, my actual process mean is between sample mean plus 0.6 mil and sample mean minus 0.36 mil during those 2 hours of production. So my actual process mean is within the range of a sample mean plus minus 0.36 mil under the assumption of normal distribution. Over here, the assumption of a normal distribution implies there's no any assignable or special cost occur during those times. If for this 0.36 mil we think actual process mean, it's not a good enough estimation for my dimensional control strategy. I will need to either increase the sample size or reduce my process variation to have a narrower 95% confidence interval. So, for example, I was talking about you can increase the sample size So the example of increasing sample size, if this is currently where we are, if we increase the sample size, but my sample 6 sigma still 3 millimeter, if I increase my sample size to 18, you can see now my estimation is about within 0.25 mil from here, horizontal to here. So that's about this value. So that's the example of increase in sample size. Another way, I can reduce variation by proactively working on my continuous process improvement methodology. So this is where we are. If I'm able to reduce my process variation, which will reflect on my sample variation. So if I reduce my variation down to this line, the orange one is 6 sigma 2. So if I'm able to reduce my variation from 6 sigma from 3 to 2, my mean estimation also is within quarter mil. So that's the first way that you can utilize in this chart. And example 2 is a different way, which I can set my target to begin with. If I would like to attain 6 sigma value equal or less than 2 mil for my process variation and achieve the mean estimation within 0.15 mil. So I can draw a vertical line beginning from vertical, I can draw a horizontal line beginning from my vertical axis. 0.15 mil is my point, is my mean estimation target. Horizontal line intersect with a 6 sigma equal to 2 millimeter curve. At the intersection point, draw a vertical line down, n equal 22. So I will need to measure 22 parts. After I finish measuring 22 parts randomly from the assembly line, for example, within 4 hours or 8 hours, I calculate sample 6 sigma. If the sample 6 sigma is higher than 2 millimeter, which means I either accept that's my mean estimation target from 0.15 to be higher, or I can increase my sample size to have a narrow 95% confidence interval. So this is the 95% confidence interval of mean estimation versus the sample size. The next slide shows the 95% confidence interval for sigma estimation versus the sample size. The vertical axis, let me move on to the next slide. Okay, so this is the slide with a 95% confidence interval for sigma estimation versus the sample size. So vertical axis is the ratio of sample sigma to process sigma. Horizontal axis is the sample size. Those two curves in the chart in the middle are the upper and the lower value of this 95% confidence interval. If I use the example from, if I use the example 2 from above, with a sample size of a 22, the ratio of the sample sigma to process sigma is between 0.7 in here and 1.3 in here. which means if my sample sigma is 2 millimeter, the actual 6 sigma is between 1.4 and 2.6. If this range is too wide for your dimensional control strategy, we can increase the sample size to have a variation estimation closer to actual 6 sigma variation. For example, if I increase my sample size from 22 to 41, the ratio will narrow from between 0.7 to 1.3, will narrow down to between 0.8 and 1.2. I'm going to conclude my discussion using the following guideline. First one, in these two charts, we are estimating process information using sample data. Theoretically, this process data is the population of the part. Population can be lifespan of the part you are producing, which can be up to 2 to 3 years. However, when we apply those very, very strict statistical theory to real engineering applications, this population can be a day of a production, even a shift, 4 hours or 2 hours of a production. It all depending upon how long you can wait before you want to know your process performance. The second guideline is those formula we use to create those two plots are under the assumption of a normal distribution for the population, which means there's no assignable spatial causes occur during those hours production when you are doing your sampling measurement. No tooling move, no mean shift in the process, and so on. The last guideline, as I mentioned, we are trying to apply statistical theory to our engineering applications. So even though normal distribution is assumed from those theory, a lot of time, a little deviation from normal distribution still give us very, very good estimation using sampling strategy. I did use this strategy to draw some sample from one of the inline 100% inspection data set. The result shows very good, which means less than 5% of the inspection entity doesn't follow those two slides I have. And guess what? Those 5% of point doesn't follow the slide. If you look at the run chart, they are either bimodal distribution from their process or their mean value. I mean, the data actually drift down and going up. That's why, of course, this theory will not apply very well, as I kept mentioning, no assignable, no spatial cause occur during those time when you do your sampling measurement. Okay, next I will turn the discussion back to Rick.
Thanks, Jim. Well, I think everybody understands why we're going to have a Q&A session after this. But first, I think it's important to note that one advantage of a nearline system over an inline system is that you can measure product from multiple lines. Obviously, with an inline system, you are measuring what is being produced in that line. And in many automotive assembly plants, there's often only one framing line and one underbody line, et cetera. So this is not much of a limitation. But in many manufacturing facilities, there are multiple manufacturing lines making different parts. And being able to measure them all on a flexible, accurate robotic system that is near those lines can greatly increase productivity and quality. This actually makes the speed of the system even more important because now the number of manufacturing lines that a near-line measurement system can service is defined by the speed of measurement. It's important to evaluate 3 additional factors when applying the statistical theory Jim just went through. To your specific measurement strategy. These 3 factors will help you determine your population size. In Jim's example, it was recommended that the sample size be 22 for the population and that your population be 2 or 4 hours of production. The math is clear that 22 samples are required in this example, but determining the population is an exercise in risk management. The 3 additional factors are your product's complexity, your process complexity, and your cost of failure. Said another way, risk can be low, but costs can be high. And the flip side is risk can be high, but costs can be low. Your product and process may be relatively simple, but if the cost of failure is that you have to do the repairs on the dealer's lot or in the customer's home, you will want to adjust your population size or time accordingly. And of course, if there is little or no cost of failure, then the population can be much larger. So let me see if I can pull all this together with a story. After I did tooling repeatability studies for about a year, my manager decided to cut me loose on a system install. And so on my first install of a system in a plant, by chance, it was that plant's first Perceptron system, and they didn't want it. They had a plant floor CMM that they would cross-transfer parts out of the assembly line, shuttle them into this CMM, and then shuttle them back out after they had been measuring for about 3.5 hours. But this Fanimation CMM was on its last legs, and they wanted a new one. And instead of getting a new one, they got a shiny new Perceptron system from corporate. Now, don't misunderstand me. These guys were great. They were smart. They were competent. And there was no hostility, but there was a pile of skepticism. So we get the system installed, and these plant guys are really looking forward to the first correlation study with their CMM because they thought it would be a huge failure. They were going to take that failure back to the corporate guys and maybe try to trade their Perceptron system in on a new CMM. But of course, you already know that result because I'm still here with Jim giving this webinar. The correlation looked great. Well over 95% of the features tracked perfectly. And even more surprising for the plant folks was the fact that more than half the measurement discrepancies between the 2 devices were flyers on the CMM side, not on the Perceptron side. So we get this first model launched and I go home, but I'm back in a couple of months to add the second model. And this sign is on the wall next to the process manager's office in the body shop. And I ask him about it, and he tells me that the Perceptron data has taken all the emotion, all the drama out of meetings with his final assembly customers and his stamping partners and his first-tier suppliers. Instead of all the stakeholders arguing about where the problem is because they don't have enough data, and of course, without data is obviously the other guy's quality problem, they were using the Perceptron data to actually root cause and fix those problems. And so what we're saying here today is that if you can measure fast enough, if you can get a statistically significant sample of what you are building on a regular interval, it gives you enough data to know what you are building and what your process is producing. And you have the data you need to constructively work on manufacturing problems. Thanks everyone for your time and attention this morning.